from Alison Poulston from JBA Risk Management, who I'd like to introduce now.
Morning all. So thank you very much for inviting me. I'm Alison. So I'm from a corporate company, JBA Risk Management, and we provide flood risk data, analysis, and models to industry partners. And I would introduce to you all of the kind of outcomes of flooding, but Richard did a pretty good job yesterday of quoting some numbers of losses at you, so I won't repeat that. We've got some images here that just show you the burned or the R Valley event from 2023 in Germany, so that you can kind of see the impacts there. And I will tend to default to talking about kind of financial losses and kind of insurance use cases, but equally any of this kind of framework can be generalized to any other kind of risk metric that you might be interested in, such as the environmental ecosystem impact, but I will default generally to economic. So any company that works with natural hazards and what we call catastrophe modelling will have some form of this diagram that they put in all of their slide decks. And I'm not going to talk through it massively because I'm only going to talk today about a few elements of it. But when we talk about catastrophe models, what we're generally meaning is a Monte Carlo simulation of some sort of natural hazard that's going to tell us about the distribution of some sort of impact. In the financial industry, we'd be thinking about the kind of monetary loss of whatever natural hazard event we're interested in. And generally, we're looking over a timescale as well. So in the financial industry, probably an annual timescale there. So we want to think about losses over a year. So a Monte Carlo simulation is going to give us that probabilistic view of what the distribution of that loss is. And the key statistic that we're interested in at the end of that is some sort of exceedance probability from that distribution. Typically in a financial setting, a regulatory constraint would be to know what your 1 in 200 year loss would be. So like in that Monte Carlo simulation, that's the statistic of interest. If you're in something like a construction industry, you've got other constraints that are maybe around the 1 in 10,000 year loss. So there's kind of different regulatory demands on different industries. But I'm gonna simplify this today, and we're just going to talk about two main parts of that diagram. So on the left, I've got what I'm referring to as our large-scale modelling. So when we're looking at this, we're thinking of the kind of spatial scales of kind of reanalysis data, so maybe like 10 to 30 kilometres. And if we're thinking about flooding, then the primary driver of that is going to be meteorological, and in particular things like precipitation and temperature. So we've got a simulation on the left there of a winter season in terms of precipitation at that kind of 30-kilometre resolution. And because I'm interested in flood in particular, we're also going to think about the hydrological response at that spatial scale. So the second set of images that I've got here on the top is the Elbe basin in Germany, which is a major river network. It runs, it's impacting cities like Hamburg and Berlin and Prague. And we've just got the main trunk there highlighted of the Elbe, and we're going from the red downstream, upstream that's at the bottom to the downstream at Hamburg up at the top there. And the image that's then replicating that colour scale at the bottom is the hydrological response across that main trunk of the Elbe over that winter season that's cycling through with the precipitation on the left there. And hopefully you can see that then, coming back to the title of this talk, there's an awful lot of spatio-temporal dependencies going on in here, right from the start of the process with your meteorological variables into that hydrological response as well, because your catchments are kind of, they're all interrelated to one another, and you've got this kind of temporal dependency where you're not going to peak in Hamburg if you've not yet peaked at Berlin beforehand. So there's a lot of dependencies in there. So that's our kind of large-scale modelling, and I'm going to talk about that in one half of this morning. And then I'm going to talk about another part of our workflow, which is focused on the local. So rather than that kind of 30-kilometre resolution, we're now really interested in the kind of 5 to 30-metre resolution. So really, if we're interested as an insurer, say, in our property, we really need that local spatial resolution. And so when we're thinking about that scale of modelling, we're wanting to convert the information that we've got on the left here to, well, we've seen the hydrological response down the Elbe. Maybe we know that it's going to flood, but what does that then mean for the terrain around it? So how does the water that's flooding actually move across that terrain? What are the kind of like the extents and the flood depths that you would get there? And if we're thinking in that default financial mindset, what's going to be then the damage to a property? Because we might have that there is a 10-metre, that's quite a large flood, we might have a 2 to 5 metre flood or something, but the impact that that has is very different if you're talking about a basement flat to a 10th floor flat, and even just the kind of construction quality or something of the property. So there's an awful lot of kind of assumptions and modelling and uncertainty to put even in that very final step of, I know it's flooded this amount, but what does that actually mean financially? So that's what we're thinking about hyperlocally on the right here. And just to kind of continue that narrative in the images, we've got a picture here again of that whole Elbe basin. If we take that winter season that's cycling through on the left, and we make an assumption that kind of 20 centimetres of flood depths is impacting a person, and we've got population data, then that image there with the red colour scale is just telling you kind of the numbers of people that are impacted during that winter season by flood risk. So we've got that story, and today I'm going to split into these two elements because we're kind of tackling these in two different ways, and there's kind of positives and negatives to each of them that I'm going to talk about. So what's kind of happening that's exciting in AI in those two fields, and where are we kind of struggling with it a little bit. So on the kind of the large scale systems, that's really where an awful lot of people that we've heard over the last day have done lots of work for us. So we can take existing work and we can put that into our use case. So to kind of step back and talk about how we have traditionally done this, we're interested, like I said, in that big Monte Carlo simulation, and we're interested in statistics that are at very high kind of parts of your distribution. If we're thinking of a 200-year exceedance there, so if you had something like this output from that Monte Carlo simulation, we're really interested in the tail, and the historic information that we've got is maybe reanalysis data 40 to 50 years. If we're interested in accurately understanding if we want to understand the uncertainty around 200 years, it's not enough. So what we would generally do would be to create this Monte Carlo simulation of statistical events, and they're going to use kind of multivariate spatio-temporal models. We generally use models that were kind of parametric extreme value because we're interested in the extremes there. And we'd create something of the order of maybe 10 to 50,000 years worth of simulations. And so if we think of the alternatives with kind of physical modelling, we just do not have the kind of computational resource to do something like NWP here, which is why we've always fallen back on statistical modelling. So now how is kind of AI changing the approach that we can take to that Monte Carlo simulation? We had a bit of a doom slide from Doug yesterday that was like a bullet-pointed list of all the failures of AI models still and how they're not really doing what we want them to do. I've got the equivalent that's trying to be more optimistic here and kind of saying they're doing a pretty good job of some of those things now. So in terms of our use case of these models, generally they're built in terms of how can we do accurate forecasting kind of in that medium range. That's actually not the use case that I primarily want them for. I don't need them to be a very good forecaster, but I need them to stay stable for a long period of time, because if I'm looking at an annual scale, that Monte Carlo simulation doesn't just want to be a collection of independent events. I really need to know whether those two massive events that are in that collection can happen in the same year or not, because that's kind of the kind of aggregate scales that we're looking at. So we want this kind of stability over long rollouts because we want to be able to run these simulations for kind of seasonal, annual kind of timeframes. And we want them to have the extremes in there, which is kind of a given for flood risk. And obviously now they're getting pretty computationally cheap. So this is an example of the model that we are now currently using, which is SFNO, because it has that kind of stability baked into it. And this just gives you a general kind of framework for how we can then put that into a flood risk modelling chain. So you can have some sort of weather simulation, put in whatever one you're interested in on the left. One of the points that I will stand by from Doug's doom list is the fact that these models don't usually produce the variables we need. So for flood risk, we're really, like precipitation is our key metric, and most of these models do not produce that. So we're going to have to bolt on some sort of diagnostic model that's going to turn those atmospheric variables into precipitation. The talk that we saw at the end of yesterday about wind gusts, these models are going to produce wind speeds, but they're not going to produce gusting speeds. So if you're interested in whether some roof tiles are going to come off, as an insurer, you need that wind gust. So you're probably going to want a separate diagnostic model for that. And you might need something like downscaling. So you could apply that in that setting too. And then we've got that dependent process that we saw before, where we take those weather variables and we look at what's happening in the river network. So we've got that kind of framework now that could use AI modelling rather than a statistical extrapolation. And is that working well? So there's kind of two big areas that we're interested in. On the left, are we getting the kind of underlying climatology, and are we representing extremes? Because extremes is really the thing that particularly my clients are worried about in terms of whether AI weather models can handle that. So just to kind of talk through this image, on the top left there, we've got the underlying climatology in this Elbe region. On the very left, you've got reanalysis data. In the middle, you've got our classic statistical extrapolation. On the right, you've got using an AI model. So we're getting that underlying climatology. On the bottom here, we're looking at the spatial correlation, but not in terms of the climatological mean, but in terms of the extremes of precipitation. So is the model representing the extremes between sites well? And again, you're seeing that you're getting agreement between that with the AI model. And the big thing that we want to do is create variability. That's why we want to create these large kind of 10,000, 50,000 year samples. And on the left here, I've just got a low dimensional representation of the events that we're seeing. The green cloud of points that's very constrained to the left there is the historic reanalysis data. And then in orange, you're seeing these kind of planes through that space, because the statistical extrapolation is going to be constrained in where it can kind of go in that space, because it's a parametric model. But the blue points then is using an AI model, and you've just kind of filled in the gaps there. So that's exactly what we wanted to see. So it's working well for our use case here. But then that also opens up some other use cases that we weren't ever able to do with a statistical extrapolation. So on the left here, I'm talking about counterfactual analysis. So if we have a known event in history or stress testing, we might have certain scenarios that the financial industry is particularly worried about. So something that impacts the Thames barrier, something like that. We can actually use the AI model, because they are now doing a decent job of forecasting with that skill. And we can explore counterfactual analysis there. The images that we've got here, I'm not going to talk about them in detail. If you go on JBA's website, there is a blog about this. But that winter season in the Elbe region, we've done a counterfactual analysis on this to look at kind of how much worse could that human cost be for that season from what it was. On the right here, we've just got an example of the fact that the forecast skill of these models is becoming better, and that allows us to start doing things like early warning systems. We can start exploring different types of financial insurance. So the classic insurance that you'll be familiar with, where a property is damaged and you get some money a few months down the line from that. That's not really a model that works in developing countries, and instead we want to be doing things like parametric insurance, where The idea is to get money input to the community as kind of the event is happening to aid in that initial response. And so that type of insurance is not based on someone coming and assessing the fact that your house is full of water. It's based on trigger systems of precipitation. So you need kind of a live monitoring system that's active all the time to see whether or not that's going to trigger. So if you've got something that's computationally cheap to do forecasts of, you can be kind of assessing constantly whether or not these policies are likely to enact. So there's kind of these really new use cases that we can be looking at there, which is quite exciting. So at that kind of large scale area where we're utilising work that others have done, this is great for me because I've got access to kind of the best models that are out there from really great research institutions, and it allows me to not spend that time developing those models. But there's some kind of challenges that come along with that. My use cases may be different to some of the other things that we've talked about, what those models were actually developed for, and we have kind of little influence in terms of the development and priorities in that area. And it also means that we're reliant on the validation that those initial research teams have done. If we're in kind of, if we're working directly with them, so when we worked with NVIDIA with the SFNO AI model, that's great because you can kind of work with the people that are developing the models, and you can kind of preempt the type of questions that my clients are going to ask, such as AI models don't represent extremes, and you can kind of design validation at the start. But if you're very kind of removed from the developers of the model and you really are just taking it kind of as a third party, you're very reliant on whatever validation they have produced. We talked earlier about how we don't get precipitation, and so we end up having to have these kind of Frankenstein models of kind of multiple things one after another. And the big problem that we've got with that then is that we're not propagating any of the uncertainty from any of these models, and we're not kind of thinking about the different assumptions that are associated with each one. And if we go back to the kind of big use case here, that we want to do a Monte Carlo simulation that's exploring uncertainty, we're actually ignoring an awful lot of the uncertainty that's going from one step to another there. So that's kind of my big bugbear with this general approach here with kind of fragmented modelling there. So now I'm going to go back to that initial slide where we talked about the two areas, and we're going to talk about the other side of things, where we're doing things locally in the flood modelling space, and we don't have something that we can effectively pick up from another research institute. So then we kind of have to go into that realm where we're developing things ourselves. So in terms of this concept of flood mapping, where we're wanting to think about how we know how much water is entering a system, but we want to model how that water is going to move over the ground itself. Traditionally, we have done that with physics models. At JBA, we have our own in-house model, JFlow. The company, that's what started the company, was that model, and that's already been kind of optimized as much as possible. The kind of company's inception was optimizing that to run on GPUs. And even with that optimization, it's extremely computationally intensive to do this. And it means, again, that we're in that restricted case where we generally do not do any uncertainty or sensitivity on the input parameters. We will do a single run of an area. And the inputs to these models are generally things like a surface terrain model. So as they get updated, I should say that we model, we do flood maps for the entire globe. So in terms of kind of updating those data sets, when something is this kind of computationally intensive, the kind of roadmap of you've got an update on your kind of terrain information, but to get that update in for the entire globe, you're kind of having these like multi-year roadmaps for updates. So it becomes quite kind of burdensome and slow to do this. So there's kind of two ways that we might think about improving that process. The first is the inputs. What I've got on this image here. On the top left, we've got a terrain model that's very smooth. On the right, we've got a terrain model that's based with an awful lot more LiDAR data. And on the right, on the bottom of those, you've got a surface water flood map that's built from those inputs, and you can kind of see the difference that makes. And it's kind of it's not even an unappreciated fact, it's an appreciated fact that the quality of a flood map is always largely determined by the quality of the DTM going into it. And then you've got all the other things associated with that. So if you need to get your bridges kind of edited before you do a hydraulic modelling, because you need the water to be able to flow, and obviously that's not represented in a classic view of a DTM. So you've essentially got here a list of image processing tasks, and you can chuck kind of really like well-established AI models at each of these problems and get a really good result. And you can kind of do that in-house so that you've got your kind of hydrological specialists that are kind of feeding in, the same way as what Stephanie said yesterday, where like when you're building these models in-house and you've got your kind of domain experts, they can like really feed into what's important in that modelling. And that kind of second way of approaching the flood modelling is the flood model itself. So, like I said, we've optimised it as much as we can, but it's still very intensive. So, can we actually have an AI emulator of the hydraulic model itself? So that's we've developed that in-house, and there's a reference there for that process. And it's really kind of the key to that. It still trains on our maps, so it's not that we're going to stop doing that physical modelling, but it unlocks some of those things that were kind of the crunch points. So how long it takes to get an update out when we have new data as input, and how we can start exploring some of the kind of sensitivity of those inputs that typically we would only do a single fixed run with. So that's kind of a really interesting point from that. But when you're kind of doing this in-house modelling, like what's then the kind of restrictions on that? Yes, it means that we can have that domain expertise, but we're very limited then in a number of other areas. We wouldn't be able to train a model of a kind of complexity of an AI weather model. So the models that we are training are kind of an order of magnitude simpler. So you're restricted in that setting. And I'd say that the biggest issue really with kind of small, medium-sized companies is the kind of multidisciplinary teams that are required for these solutions. So you can have your kind of domain flood experts, you can have like your AI experts, but if you've not got your machine learning engineer that's actually going to mean that an epoch doesn't train in a week, it trains in seconds. Like all of that kind of infrastructure and having that multidisciplinary team is really challenging for kind of small companies to meet that that kind of like full ring of kind of skills that are needed for that chain. So I think that's really the issue there. Potentially another point as well with when you've got these fairly kind of simple separate image processing tasks, it can be very easy to chuck a unit at every single one of them, make it slightly different, and then you suddenly have a company that's got 10 different models that you need to maintain, and you create this technical debt for yourself very, very quickly. So that's maybe another hazard of being able to do some of this in-house yourself. So I just want to end today back with the kind of horror image of all these parts that are going into a catastrophe model. We have these very fragmented systems, and we can utilize kind of the newest exciting models to address certain aspects of them, and we can build models ourselves to address certain aspects. But it becomes this kind of convoluted system, and that's even just looking at what we produce in JBA. We've then got a set of customers that have customers, and they themselves have got regulators, and they're all using our model in kind of different use cases in different ways, and we don't always know how that is. So in terms of whether or not my kind of talk about this fragmentation and this kind of lack of uncertainty propagation, whether that's leading you to think that we should have a foundational system, that's not me saying that we should. We spin off products at every single stage of that modelling process, and we have different use cases at all those stages. And so that kind of concept that we could solve this just with kind of one big simple model, we're maybe not there yet. And the kind of trust as well within your customers and their regulators. So just in the financial industry, that regulation is quite slow moving, and there is a distrust of kind of AI and AI weather models themselves. So kind of how you deal with that, and the need to explain the specific answer that a company is going to use for their pricing to their regulator is really important. So that's where I'm going to end today. I feel like that was a bit of a low on foundational models, but yeah, thank you very much.